Okay, so next we have air masses, fronts, and storms. That's what we want to talk about next. And so we're going to start by talking about air masses, which fall into six categories. And there's a table here from your textbook showing classification of air masses and their characteristics. And so you can talk about the maritime polar classification, which comes from the North Atlantic and the Pacific Oceans. Um, it has characteristics of being cool, moist, unstable. I'm not going to go through and read everything in this table because you guys can all read, but just know that there are these different regions and they lead to different air masses. Here we see some different air masses connected to their different regions. So, for example, here's the maritime tropical. Um, Also, here we can see the maritime polar, the continental tropical, etc. Um, these are different regions of air which interact with one another. Obviously, the air in some areas is going to be colder. The air in other areas is going to be warmer, and of course, we have currents that are pushing these air masses together. So sometimes they're going to interact, and that can create a variety of weather conditions. Now, one of the great indicators of different types of weather are, of course, are clouds. And in order for clouds to occur, they have to be the air has to be lifted upward. There has to be what we call atmospheric lifting, the lifting of the air. And there are three different ways that you can get atmospheric uh, lifting. There's what's called convectional lifting, there's what's called orographic lifting, and then there's what's called frontal lifting. And we want to take a look at these. Now, the first type of lifting is called convectional lifting, and that uses the process of convection. So the idea is this: so the sunlight is coming in and it warms the ground up. So the air near the ground is warm, and so it expands, it gets less dense, and it rises. At the same time, the cooler, denser air up above sinks downward, and that pushes that warm air up. Now, that warm air has more water. Remember that warmer air can contain more water. And so that warm air is being pushed up. As it goes up, it cools. And so that water that's contained in that warm air condenses out as the air cools, and that forms clouds. Another kind of lifting is called orographic lifting. And this kind of lifting occurs when the air is pushed up over an obstacle. So, for example, we've got we have sort of a coastline here, and then there's this mountain range, and so you have a prevailing wind coming in from the sea. You have moist, warm air that's rising, and this together pushes the air up over this mountain range. Now, as it goes up, it cools, and you can get cloud formation and even rain. Now, often what happens is the rain forms over here, and so all the water condenses, well, not all, but a lot of the water condenses out of the clouds as rain. And so what comes over here is cool air that's had its moisture taken out of it. So the air is much drier over here. And so for that reason, because it doesn't often tend to rain on this side, this region is considered what we call the rain shadow. It's in sort of the shadow region where you're going to have much less likelihood of rain. But this obstacle is basically the mountain range is acting as an obstacle as the wind is pushing it forward. It actually guides the air upward, and that's another way that you can get lifting. And the third type of lifting is what we call frontal lifting. Now, you've probably heard of weather fronts if you've ever watched the weather report on the news at night. They talk about there's a warm front moving into the area, so we can expect rain or whatever it is. Have you ever wondered what they mean when they talk about a warm front or a cold front? Well, a front is simply the contact zone between two different air masses. You've got two different air masses and they're coming together and they're interacting with one another. And that region where they're interacting with each other, that's what we call a front. So let's look at how this can lead to lifting. So imagine you have a cold air mass and it's moving and it's converging with or interacting with a warm air mass. Well, as the cold air mass moves into the warm air mass region, we know that the cold air is denser, it's heavier, it's going to tend to want to stay low. The warmer air wants to rise up. So as this guy moves here, it's going to kind of push underneath the warm air and lift it up. Now, of course, we know that as this warm air gets lifted up, it holds more water. I'm sorry, that's my dog Charm. She says hello. Anyway, as I was saying, um, as this warmer air is pushed up, it cools down at the higher altitudes and it's not able to hold on to all the water it contains because we know that the amount of water that the air can contain depends on its temperature. So the warm air cools up here, it forms clouds and can lead to rain and precipitation and thunderstorms, and we're going to talk about those as well. Now, here we have the opposite case of a warm air mass moving into a cold air mass. And of course, rather in the previous slide, we saw that the cold air mass moved in and pushed underneath the warm air mass and pushed it up. Well, here, the warm air mass, as we know, warm air tends to rise, it just kind of slides up the cold air mass. And so this tends to be a more gentle shifting of the conditions. And you can see that as the warm air front moves up, the different types of clouds form according to their altitude. So we know the nimbostratus and the stratus clouds are in the lower region. You get altostratus and cirrostratus, and finally cirrus clouds. All these kinds of clouds form as they move up in altitude, as the warm front sort of gets pushed up and over the cool air mass that it's moving into. The next kind of front we want to look at is what's called an occluded front. And so you can imagine that you have sort of a cold air mass up here and you have a warmer air mass coming in from underneath. And this creates almost kind of a cyclonic action as this air is pushed around and it kind of loops over here. And so what you end up with is this warm air is separating into the cold air. And so you can see that if you look at this as sort of a cross section, that you have a region of cold air pushing in and a region of cold air, and the warm air is tending to lift up and rise. And eventually what happens as these guys merge, this warm air region gets pushed up above the ground. And as the cold air continues to move in, that warm air gets pushed higher and higher. And so the cold air completely wedges underneath. And as the warm air rises, of course, you get cloud formation and rain. And this kind of merging of fronts can create storms over very large areas. So this is something that can greatly affect weather patterns. Damn it. Now the next thing we want to talk about is a cyclone. A cyclone is an area of low air pressure around which winds flow. Now, due to something called the Coriolis force, winds in a cyclone move counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. So what does that mean, the Coriolis force? This is actually a pretty complicated topic from physics, and I'm going to briefly explain how the Coriolis force works, but if you don't fully understand it, don't worry about it. I'm just, for the sake of completeness, I just want to describe basically how it works. And so let me give you an analogy, or rather a different example. Okay, I've got a circle here that is representing the Earth. And imagine that you're on a ship and you want to fire a shell and you want to strike another ship that's miles and miles away due north of you. You're going to fire your shell and you're going to have that shell go north to hit the target. But the problem is, after the shell is launched, that target is on the Earth, which is spinning about its axis. And so the shell wants to go due north, but by the time it would hit the target, because the Earth is rotating, the target is now over here somewhere. And so if you don't correct for the Earth's rotation, you're going to miss the target. From the perspective of someone underneath the shell, watching the shell from its initial launch point, it looks to them as though the shell has been pushed off to the side, because the person that was the target, or the ship, or whatever that was the target, has been rotated over by the Earth. It's almost as if a force has pushed the shell out of the way. It's not actually a real force, it's just the fact that the Earth has rotated out from underneath it. And so basically you get the same sort of effect here, that as the air masses move and the Earth is rotating out from underneath them, it can create a tendency for this kind of circular motion. And as you get this kind of cyclonic action, that causes a convergence of the air in the center where the pressure is lowest, and the air is forced to rise upward. So just to remind ourselves, what is the name of the kind of front that occurs when a cold front and a warm front merge? Well, the answer is that is an occluded front. Now, there's another thing here, an option, convection. That's a cause of lifting. That's not a kind of front. Turbulent, that has to do with the way that air flows, but it's not actually a front. There is something, though, called a stationary front. What do you think a stationary front is? Guess what it is? It's a front that's not moving. So if you ever hear someone talk about a stationary front, it's pretty obvious what they mean. But again, just to recap, what is the name for a front that occurs when a cold front and a warm front merge? We call that an occluded front. Now let's talk about storms and violent types of weather. Now, storms are defined as violent and rapid changes in the weather. That's what we mean by a storm. And there are three major types of severe storms. There are thunderstorms, there are tornadoes, and there are hurricanes. Thunderstorms begin with humid air rising, cooling, and condensing into a single cumulus cloud. When fed by unstable, moist air, remember, unstable air, that's when you have a rising of the air and it doesn't come back down. As you get this cumulus cloud fed by this rising, unstable, moist air, the cumulus cloud grows into a thundercloud. And then thunderstorms occur when you get the precipitation. And thunderstorms contain immense amounts of energy. Now, all thunderstorms include thunder and lightning. And lightning is simply a flow of electricity. It's the same process if you've ever been zapped by a doorknob after you've scraped your shoes across a carpet. You see that little arc of electricity between your finger and the doorknob. That's a little miniature lightning bolt. The same thing happens with clouds. Now, what's happening when you touch the doorknob? You've walked across the carpet and you've scraped some excess charge onto your body from the carpet. And that charge gets released to the doorknob. The same thing happens with thunderclouds. Thunderclouds become charged. There are ice crystals in the clouds that are rubbing together. There's dust in the clouds that's rubbing together. This creates an electrification of the cloud, and it builds up a tremendous amount of charge. Now, normally, air is an insulator. It's a material that doesn't allow current to flow, but these clouds get so charged, so vastly charged, that the air underneath them, the electrons start to get literally ripped off the atoms and turned into ions. And that ionizes the air and causes the air to become electrified. And when that happens, the air is no longer an insulator. Ions in the air enable the conduction of electricity from the cloud to the ground. It's interesting, actually, it can also go the other way. You can actually have lightning strike from a cloud up, from the ground up to the cloud. And of course, you can have lightning go from one cloud to another cloud. but this is essentially a flow of charges that represents a tremendous electrical current. Now, as the lightning flash happens, it releases a tremendous amount of energy and it heats up the air tremendously. And the air expands explosively, and we hear that as a thunderclap. Now, a tornado is a funnel-shaped cloud of air rotating around a low-pressure core that reaches from a cumulonimbus cloud to the ground. There's also something called a funnel cloud. It's basically a tornado that doesn't touch the ground. And of course, we know tornadoes are very dangerous because they have tremendously high velocity winds and it creates a tremendous amount of suction. But actually, the biggest storms that exist on Earth are hurricanes. And hurricanes occur from energy that comes from the latent heat released when you have condensing water vapor. So you have rising warm air that creates low pressure near the surface, which draws in more moist air. The winds rotate around a low pressure area, which was called the eye of the storm, and there is a continuous supply of energy from tropical waters. The hurricane actually will weaken if its fuel source, that heat, is cut off. And as it makes landfall or if it enters a region of cooler water, that robs the hurricane of some of its energy. But as it moves over these tropical waters, it can gain in tremendous strength. So this happens in sort of stages, where so you can have strong vertical wind shear, which can cause warm air to tilt inward and create sort of a spiraling effect. And that is the first stage where you create what's called a tropical depression. And as that storm intensifies, it becomes what's called a tropical storm with increasing wind speeds. And eventually, if it gets strong enough, it becomes a hurricane. And hurricanes can have wind speeds up to 300 kilometers an hour, which is crazy fast for wind. So, what is the eye of a hurricane? The eye of a hurricane is an area of low pressure. Now, it generally occurs at the center of the hurricane. So if you have a hurricane, which is swirling around, there's a region kind of in the middle where there's low pressure. The highest winds are out towards the edges, but when you're in the center of the hurricane, it's actually calm. And so you can imagine, if here's your coastline and the hurricane's moving in, the edges here hit and you get really, really high winds, and then the hurricane moves in, you get the eye, and so you get high winds, and then it gets calm, but then the other side of the hurricane hits and you can get high winds a second time. Now, as the hurricane moves over the land, it tends to lose a lot of its energy and disperse, but it can create that sort of double whammy. But the eye is that calm region of low pressure at the center of the hurricane. Now, lastly, we can talk about weather forecasting. And weather forecasting involves collecting data about different weather patterns from all over the world, and computers can plot and analyze that data to predict the weather, although the many variables make accuracy difficult. One of the first people to actually sort of describe this process used in weather prediction is someone you've probably heard of before, a guy named Benjamin Franklin. When Benjamin Franklin was Postmaster General of the United States, he got weather reports from all over the country carried through the mail system. And he started noticing things like, there would be a storm at this place one day, and then the next day there would be a storm here, and then the next day there'd be a storm over here, at these different towns. And he realized that if you had enough information, you could track the storms. And so, if a storm's hitting this town and you know which way the wind's blowing, you could predict that the storm's going to hit over here in a couple of days. And so the people over here could prepare for the storm or whatever. That basic idea was the foundation of the science of meteorology. But even as sophisticated as all of our computer models are and as powerful as our tools are, weather prediction is kind of a iffy proposition at best. we can do pretty good job predicting weather out a few days, but once you get beyond a few days, because of the complexity of the weather system, it gets harder and harder. And it's actually impossible to predict the weather for more than a couple of weeks, just because of how chaotic and complex the different weather systems are all over the world, and they're all interacting with each other. And so we've come to the end of our PowerPoint and the end of our lecture, but hopefully you have a better understanding about some of the factors involved in how weather is generated.